Hi everyone, thank you for joining AWM Pitt Grad Seminar. Today we have two speakers. Our first speaker is Emily Winn from Brown University. Her talk is revisiting the effects as analog for variable selection in nonlinear regression. Our second speaker is Himani Sharma. She is a PhD student from Australian National University. Her talk is boundedness of certain square functions. And Emily, you can go first.
Thank you very much for the introduction. So the title is a little bit misleading because we did research, and as things happen in research, sometimes things don't quite go the way you thought they would, but you end up finding something else in the process. So today I'm talking about revisiting the effect size analog for global and local variation. This is a quick outline of my talk. I'll first go over some motivation and background. I'll then talk about our methods and our contributions, and then I'll talk about some preliminary experiments and results that we have. And this is work with my advisor, Dr. Lauren Crawford, who's at Microsoft and Brown, and our collaborator, Dr. Mary Claire Griffin, who is a professor at UMass Amherst. So with variable selection, this is a problem that applies to pretty much any type of data science or information collection that we have. So for example, we look at what factors affect a certain outcome and what is the size of that effect. And this can be asked in so many different ways for so many different fields. So for example, what genes cause a tumor to be malignant, or what factors affect a student's standardized test score, or what is a company weighing when determining the price of a product. And so we want to be able to find ways to predict that outcome accurately, but we also want to be able to have transparency in how we make that prediction. Now, variation can come in different components. So we have the totality of variation. We can break this down into a feature variation, which is the signal we're looking for of like actual variables or that are driving the variation. And then noise, this is randomness, interference, things that we can't necessarily measure or account for. And then we can break down this feature variation even further into linear variation, which is the additive effects, and nonlinear variation, which are the interactive effects. So additive variation or linear variation has to do with singular variables contributing to the variation. Nonlinear variation has to do with any combination of two or more variables contributing to variation. So just some notation that we're going to be using for this talk. We have an output y, which is an n by 1 vector in the real numbers at some sort of measurement. So it's this vertical vector y. And then our data is an n by p design matrix with n samples and p covariates. So an example would be our input would be, say, the genetic sequences of a crop of corn. And then the output would be the crop height or the crop yield or different characteristics of the corn we want to measure. And so the most traditional way to measure linear variation is through a linear model. So this is the basic setup that we know and love, where y equals x times beta plus epsilon. Epsilon is an error term coming from a multivariate normal distribution, and beta sub j gives a notion of evidence for association. So here's kind of a visual of what the matrices all look like. We have a trait y, genotype n by p. So this can be any data, but we're using genetics as an example. That's kind of the perspective I'm coming from. And then the beta vector makes up the effects. And then beta j is the effect that the jth covariate has on the output y. So linear models are one way to do it. You can also use nonlinear models, which are usually black box methods. So machine learning methods tend to be well suited for prediction-based tasks. You have input, you have output, but the black box refers to statistical or machine learning methods with hazy implementations. Excuse me. With hazy implementations or uncertain internal workings. So these are methods where we don't necessarily have a weight or effect size assigned to each covariate. We don't necessarily even have numbers that we can assign interpretably speaking to the covariates. We just know that we put in data and we output data and it has a certain accuracy predictive result. So there's this push and pull between linear and nonlinear models, where nonlinear models are often more predictive than linear functions. But with linear models, the variable selection is much easier, even though it's not as predictive. We actually know which variables are contributing. So it's this push and pull where we want to be able to know, do variable selection, but we want to be able to do it accurately. And so we need more complex models to do this. And there's been lots of literature about this, especially recently with the rise of data science. So some of them do capture linear and nonlinear effects. The downside is a lot of them only capture global effects versus local effects, which are also important to capture. And I've specifically starred the rate method here because we'll talk a little bit about that later. Or they capture linear and nonlinear effects, but they don't have that natural interpretability we're looking for. And I'll go into these two characteristics in the next slides. Local effects are important because when we only look at global effects, we can actually neglect the way that data is collected. Excuse me. We can affect the way the data is collected. And this is an example from a genetics paper or a Nature paper in genetics, where the UK Biobank has mostly data with people from European ancestry, when in reality they represent less than 20% of the global population. And this is a wild statistic from the paper. Over 90% of samples in GWAS studies represent 16% of the human population. And this is awful because we're trying to use this information for medical treatment and for medicinal purposes, but it's skewed towards one continent's population. And that's a problem because that means we can miss a lot of genetic variation and we can miss a lot of information. It also is an issue when we talk about issues of personalized medicine, which is growing in popularity, at least idealistically, in cancer treatments, which we know is a genetic disease. And so therefore, how can we kind of treat with a personalized genetic approach to each person? It's difficult to do that if you're going on global information that is so skewed towards one subpopulation. And then in terms of interpretability, well, we don't have a strict mathematical definition of this. You hear this thrown around a lot. So we'll give what we care about. We want some sort of numeric value attributed to each covariate, which signifies some sort of evidence of association. We want this resulting model to lie in the feature space. So we want to be able to say this number goes with that covariate. And finally, we want some sort of natural notion of a null hypothesis. So we have a way to measure significance. It is great to assign numbers to covariates and to say, oh, this one's bigger than that one. But we still need a way to check ourselves that this actually means something. And it's important for have all of these parts of interpretability because it is key for any algorithm or statistical method to be responsibly implemented in practice. These methods allow us transparency, they allow us to update, they allow us to look at what's wrong with the model and tinker it, and also test it against real data and continue to improve it. So we aim to develop a method that is able to capture linear and nonlinear effects, that is able to do this at a local and global level, and is interpretable relative to the data. All right, so now we're going to get a little bit more into the math of things. So we'll start with the nonlinear regression models, since those are better for prediction. So before I had y equals x beta plus epsilon, now we'll just have y equals some f of xi plus epsilon, where f is just some nonlinear function. We can use what's called a Gaussian process to specify a prior distribution over this function directly. So a Gaussian process has a mean function and then a covariance kernel. So the notation of this, x sub I are the covariates for the ith sample. M is the mean function. K is the covariance function or the similarity measure between samples. And in our case, we're going to use the Gaussian kernel function, which is displayed here. And there's a couple of reasons for this. So the first is that The exponential Taylor series expansion has every single power of x. And so when we use the Gaussian kernel, we have this natural interpretation that we are taking into account every single possible order of effects. So we're taking into account every additive effect, we are taking into account every pairwise effect, every three-way effect, etc., all the way up to n. And we are also weighting those effects, so we're putting more priority on the additive and pairwise effects than the more complicated effects going on. So the covariance kernel looks like this, just to give you a visual. So it's an n by n matrix where k sub xi xj is the covariance between the ith and jth samples. The problem is if we just do this directly, you end up putting this in function space, and it's n dimensional, which is the number of samples. You can't, there's no really easy way to put it back into p dimensional space, which is what we want. We want the model to be back in feature space. And there's an issue with the kernel trick. It's hard to do that. And so the classic idea of variable selection is lost once you apply a kernel. So you have to do something to get it back into feature space. So one previous idea was to take the idea of the linear model that we had, and we have what's called an effect size, which basically means that we take the data and we project it onto our output vector y, and that gives us our beta hats, which is our prediction of the effect sizes. And usually that comes in the form of using a generalized inverse projected onto y. So in this case, on nonlinear models, what we could do, and has done, is there a question? Oh, sorry. Anyways, what we could do is what's called an effect size analog, which means we project fx onto the function of f in a similar way with the generalized inverse. Problem with this is the signal is very small, so at least in practice. So Crawford et al. In 2019 had to do more math with this. They ended up figuring out using a KL divergence calculation, but that calculation had to be computed p times. And since the KL divergence is a very expensive calculation to make, it was not a scalable method. So we're trying to improve upon that to a method that's actually scalable. Which brings us to our method, the global and local score, or goals. And so the main idea is to perturb each column j of x in the data and see how the resulting nonlinear function changes. That's our overall goal for goals. So the first step is to define an x tilde of j. And we're going to add a constant c to the jth column. In our application, we are a genetics, as I mentioned. We are going to add 1 to every single column. Here we use that because SNPs are encoded in the space of 0, 1, and 2. Adding 1 to 2 does technically put it out of the space. You can think of this kind of as modulo addition, where we're just kind of rotating the values of the jth column in SNP space. So 2 goes to 0, 0 goes to 1, 1 goes to 2. And we're going to do that for every single column, but we're focused on the jth column for now. So we've got our x tilde of j. We're then going to use a nonlinear regression model from before to calculate f and g of j. So f is going to be exactly the same. And then g of j is going to be with x sub I tilde, an error term. And these functions I forgot to mention earlier, but they are both in a reproducing kernel Hilbert space. We need that because we need some nice properties from that space to do the statistics that we want to do. And then this prior on f and g of j is going to be a joint Gaussian process prior. So we're going to have these kernel functions here. We're going to assume both are centered at 0 to start, and then we can sample a posterior, which allows us to then fit the data. Or we can sample a posterior based on the data, I should say. Quick note, this kernel k of xx only needs to be calculated once. This is because when you have k of xj, that ends up being equal to this k of xx because you're adding a constant to a covariance essentially, which does not change the covariance itself. Additionally, when we have K of X, X sub J tilde, it is a rank 1 update of B, which is what our shorthand is for this kernel. And that's part of the reason we're using the Gaussian kernel in the first place, is because since we have to calculate this P times, we need a quick way to do that so that we don't compromise computational speed for more information. So step 3 is to calculate a delta sub I of j equals g of I of j minus f of I, where I denotes the ith sample. And then we're going to repeat those 3 steps for all samples I, for all features j, and get this n by p matrix delta. So we have these deltas here. It's still n by p, as I said. And the interpretation is that when delta of j is near 0, then feature j had little to no effect on the output, because when we perturbed the feature, it did little to affect the nonlinear function. So this is our natural null hypothesis that we wanted. So going back to the interpretation of delta, we have a local interpretation where delta sub I of j is the effect that feature j has on sample i's output. And then we can take a partition, or we can partition the rows based on the subsets of X. So for example, if we're looking at genetics, we can look at subsets based on continental ancestry and global populations, which will allow us to look at the overall population, but also break it down by continental ancestries to see if there's any other variation that we should be looking for. In the global, we can take a summary statistic of every single column of J, for example, the sample mean, and use that as a summary of the J's effect on the local output. And then in terms of hypothesis testing, what we can do instead of your typical p-value, which has its own flaws, we can use what's called a local false sign rate, which was used first in Stevens in 2016 to determine a significance. So this is just the minimum probability that the mean of delta J is greater than 0 versus the probability that delta J is less than 0. And so this is what's called a type S error. It's focusing on the error in sign of the deltas. Excuse me a second. So finally, we get to the experiments and the results. So we're going to do a small proof of concept with a genetic simulation. We're going to simulate data sets with n equals 2,000 samples and p equals 25 genetic markers. We're going to choose the last 3 markers, 23, 24, and 25, to be causal, and then markers of J star have additive and interactive effects weaved into them. So both are taken into consideration. And so when we calculate the goals for this, we see that the overall delta mean values for SNPs 23, 24, and 25 are visually very far away from 0 compared to the other non-causal SNPs, which are very much hovering around 0 with their means. And just as a sanity check, we use the local false sign rate. And indeed, we find out that at a significance value of S equals 0.05, all of these significant SNPs have an S of J below that value. Meanwhile, these SNPs all have huge S of J values. So it's around 0.4, which really means it's hovering around that 0. We're pretty confident about that. So again, we have a visual showing that 23, 24, and 25 are significant, but we also have mathematical variation of that as well, or verification of that, I should say. Just as a sanity check, we also do the null hypothesis. So what happens when goals are just given pure noise or nonsense data? And we see here that again with the delta J's, they're all hovering around 0, which is good. That's what we want if we just give it noise, or none of the variables have any effect. And again, the minimum SJ value here is 0.4. So none of these are significant, and that's what we wanted to check with our method. So now we're going to do a second simulation, and this time we're going to divide the data into 2 subsets. The first subset will have the last 3 markers be causal. The second subset, we're going to have the last 4 markers be causal. And so this is kind of going back to the experiment we saw before, where we've got data sets coming from different continental populations. And so can we, if we were to divide it up and just see what the data looks like after pooling it all together, would we be able to see any differences? In particular, can we see that 22 is contributing to one but not the other? And so first we'll check that 25 distributions. This is a local distribution of all of the delta 25 values in the population. You can see that it is very much to the right of 0 and that its mean value is at over 1. So here we can say with a lot of confidence that this that the 25th SNP is contributing a lot. That's contributing probably to the majority of the population, but there are some where it's probably closer to 0. So in a personalized medicine situation, we'd be able to take that into consideration for those samples. On the other hand, local distribution of the 8th SNP, that is a non-causal SNP, you can see that it is smack centered around 0. Again, it might go in either direction, but the distribution overall says that it doesn't really affect the population, but again, it could affect it for local or for small samples, but very much centered at 0. What's interesting is that when we look at the 22nd SNP, which I call half causal here because it is causal for half the population, we find that it is shifted a little bit from 0, probably not significantly enough, but enough to cause curiosity, perhaps. The delta mean is positive. The majority of the distribution is not centered at 0 clearly. So what happens when we split this up? If we just split it without recalculating delta values or anything? Well, in fact, we actually find that the populations do kind of shift apart. So we have a population that where SNP 22 is not causal, that distribution drifts towards 0. And the population where the SNP is causal, that population drifts away from 0. And we see that with the means themselves actually starting to split up. So that might warrant, if we were actually doing a genetic analysis here, going back and examining these populations separately on this particular SNP. And so this method is awesome because it allows us to do that kind of local breakdown, whereas other methods can't. So in future works, we want to explore different possible values of C. We just used the middle value here in our SNP space, but there could be other values that we want to use based on discrete spaces versus continuous spaces, based on the actual numbers that people are finding in their data. We also understand that perturbation in function space may work well for GWAS, but not necessarily other applications. And so we got to figure out why or when it would work well, not just that it does. There's also a possibility for alternate summary statistics, such as delta J instead of the mean. We chose the mean because it is a straightforward summary statistic, but it also allows for computational shortcuts. But that might not be an appropriate summary statistic for other applications. And then here's my acknowledgements. Thank you to the Crawford Lab, the NSF for my funding support, and thank you all for inviting me in for listening.
Thank you, Emily. Does anyone have any questions for Emily?